Hey guys, welcome to Chapter 10. Chapter 10 is just going to be the hypothesis testing extension of Chapter 9. So in Chapter 9 we went from one sample hypothesis testing, and now Chapter 10 we're going to be covering two sample hypothesis testing. Okay, so the way that I'm going to cover this is I'm going to sort of equate everything back to, or transition everything from Chapter 9. So the stuff that we learned in Chapter 9, I think we learned four different types of hypothesis tests. One was the z-test about the population mean. That's where we knew sigma, or sigma was given to us. Then we had the t-test about the population mean. That's where we didn't know sigma. We only had like an s, or we had to calculate an s, right? The sigma is the population standard deviation, so that's 9.2. And then for 9.3, we just had a sample standard deviation, and that's what signified the difference between those. And then in 9.4, we moved on to the population proportion, the z-test about the population proportion. And this is when we had a population proportion. So we had an assumed population proportion of like p naught, and then a sample population proportion of p hat. Okay, so and we used the z tables, or the normal tables, for that as well. And then we learned a new distribution, which was the chi-square distribution, and that was in order to run hypothesis tests on sigma squared, or the population variance. Okay, what we're going to learn in Chapter 10, so all of those we compared to some kind of like believed value of the population parameter, right? So the population parameter being mu, or being sigma, or being p. Okay, so essentially what we did is when we started our 7-step hypothesis test, we would first write out these hypotheses, and the hypotheses would consist of us comparing our proposed mu against a number that we our proposed mu against like a number that we assumed that it would be. Okay, and so then what we did was we had one sample, and then we weighed that one sample against that proposed mu, that proposed number. Okay, so what's going to be different in Chapter 10 is that we essentially are going to have two samples rather than one, and we're going to be comparing those samples to each other. So there's no longer this like mythical proposed mu. Like there's no longer this assumption that we know something, or that there's an assumed belief about the population. Okay, the only real assumption we're going to be making is that a lot of the time we're going to assume that the population parameters are equal, and then we're going to have to prove that or disprove that. So essentially what's going to happen is we're going to be comparing the samples against one another to see if their difference is significant, as opposed to the in Chapter 9 where we had the sample where we tried to see if the difference between that sample and the proposed mu was different. Now we're actually looking at two samples and trying to determine if they are significantly different. Okay? So we'll get into that in a second. I did want to let you know I'm not really going to be using PowerPoint in this video, though I have made the PowerPoint slides available to you on Springboard, so you can go on Springboard and download those if you would like. But I'm going to be using this worksheet, which was made up by a colleague, and I think it has pretty much everything we need to know and that we're going to be using in this course. Okay, so I'm going to go off the worksheet. If you have anything else that you would like to look up, there's obviously the PowerPoint slides that I just mentioned that are on Springboard. There's your book. And within like the ebook, you can actually click in certain places and it'll bring up the book's version of the PowerPoint slides. So there's all sorts of options, and then you always have the option to email me or post on the discussion board or whatever. So I'm always here to help, and I want to answer your questions. So okay, without any further ado, let's talk about one topic that I think there was some confusion about. Recently, I had a lot of student questions on this topic in the online class and in the regular brick and mortar style class. Okay, and that concept was p-value. What is p-value? Okay, so the way that I would describe p-value, because what ended up happening is there was p-value problems on the homework. We sort of just briefly went over it, I think, in the last video, and I kind of skimmed through it and said, hey, we're really not going to need this until later chapters, and that was kind of that, which I guess it was my mistake. I just hadn't gone over the Connect homework and saw that there was p-value questions. Though I think once I describe the concept, it's not that hard of a concept. I don't know. It makes sense. Hopefully you'll get a good understanding of it from this video. But yeah, there was a lot of confusion on it. That's my fault. My apologies for that. I'm going to explain it, I guess, more now, and you're actually going to see that we do need it more in chapter 10, 11, and possibly in chapter 12, but definitely in 10 and 11, because we're going to be using more computer output and stuff like that in 10 and 11. So p-value is a probability value, and it is just used to essentially determine our alpha error, so our chance of being wrong when we run like a hypothesis test. Okay, so I'll first describe kind of what alpha is, right? Oh man, I'm terrible with this pen again. Okay, so say we have some sort of test, any kind of test. This is our normal curve. We're going to use this distribution as an example, and say we're running like an equals, not equals style test. So this is two-tailed, okay? So this is a two-tailed test, so we're going to have some critical value right here. So let's just assume it's normal. We'll say z crit is something. We don't know what it is. Doesn't really matter what it is at this point. And then we have like the negative version of z crit. Okay. Well, so if we have an assumed alpha level of something, say we're using alpha level 0.05, that seems to be something that we use a lot. Alpha level is just describing the chance that when we run a test, this is going to be the probability beyond our critical value points. Okay, so this is the probability. So first of all, because it's two-tailed, we split that 0.05 up onto each side. This is going to be the probability that when we come to the conclusion to reject the null hypothesis, that we're wrong, right? So if we have 95% confidence on something, or an alpha level of 0.05, those are synonymous, right? If we have 95% confidence on something, then we have 5% chance that we're wrong, and that's what our alpha level represents. Okay, so this alpha level helps us find our critical value, and essentially is going to be synonymous with the critical value, right? Our critical value is based off of alpha, and our alpha is based off of our critical value. Like they're one and the same. They go hand in hand and whatnot. Okay, so what you've noticed when we do these hypothesis testing problems is we have a critical value, so a z-crit in this scenario, and then we also have a calculated value or a data value, whichever I've referred to it as. Okay, so our p-value is going to be something that is referring to the calculated value, right? So we have this here. We're going to look at the same thing. Okay, so we have 95 in here. We still have an alpha level of 0.05. So we've got 0.025 here, 0.025 here. Okay, so, and we have our z-crit here, our negative z-crit here, and our positive z-crit here. Don't really know why I just wrote the whole thing out again. Maybe I just needed space. We'll see. Okay, so we have this set up, and we have this on our critical values. Okay, so the p-value is going to be based off the calculated value. So say we run a test, and we want to find out whether we reject something, and we get a z-crit value that is over here, or a z-calc value that is over here. Okay, so now we have a z-calc value that's over there. Now our p-value is going to represent the probability that's in this tail, right? So given that we've calced it, Now what is our probability of being wrong? So the alpha level is our like set value that like, hey, we're going to reject the null hypothesis if we pass certain critical values, and our alpha level sets that probability of being wrong, right? But then our calculated value is saying like, okay, now we've run the test. Now given that we got the value that we got, now what is our probability of being wrong? So the z crit and the alpha level for that, that's the probability of being wrong prior to us running the test. Now that we've calculated a value, okay, that tail value is going to be the probability that we were wrong in our assumption, in our conclusion from the test, based upon that calculation. Okay, so that's why you'll see, like, so in a case where you run a hypothesis test and you have a z value that is vastly greater than its critical value, or vastly surpasses its critical value, could be greater than a positive like z crit, or it could be like far less than a negative z crit. So it far surpasses its critical value. You're going to see a p-value that is a very, very, very small number, right? So like something like this, you might have a p-value that's equal to 0.00003 or something. And that would just simply be our probability of being wrong in our conclusion, given this calculated value that we came up with. That's it. So that's p-value. So p-value is kind of the calculated version of alpha. All right, if you want to think about it like that. So that's p-value. Now the ways that you find p-value, that's been documented, I think. When we're working with a z-test, assuming that you have a value, a z-calced value that is on the table, just go to the table and pluck out the probability that you find on the table. If it's on the left-hand side, you can use that probability. If it's on the right-hand side, you're probably going to need to use 1 minus that. Okay. All right. And what else? And more than likely, you can just get this, you can get the p-value on Excel as well, and I have described that in the discussion board as well. You can do it with Megastat. You can do it with Excel just using formulas. So if you would like to see how to do that, just check out the discussion boards, or just kind of play around with Megastat. It's fairly simple once you get the hang of it on Megastat. And Excel, it's a little bit more challenging because you have to kind of get comfortable with the function that you're using, but go check it out and try to work with it then. It'll be helpful for your case more than likely. Okay, so let's get into chapter 10. So the first distribution we're going to look at in chapter 10 is comparing two population means. All right, so this we would equate to 9.2 or 9.3 when we compared a population mean, or compared our sample to a proposed population mean. This is how the, this is how the hypothesis tests are going to look. This D naught signifies the difference that you propose is between the two populations. So more than likely, this D naught is going to be, that is not a D. This D naught is going to be 0. So, like, just to rewrite one of these hypotheses once, we're going to look at this one, the not equals one. You could rewrite this as, assuming that the difference that you propose between them is 0, you could assume, or you could write this H naught as mu1 is equal to mu2. Right, and that's just us putting 0 in for D naught, and then just taking mu2, mu2 over to the other side. This tends to be a little bit more intuitive of a way to think about it. So then for the HA, we would have u1 is not equal to mu2. And that's that. So the reason that they do the formula like this, where it's mu1 minus mu2 is equal to d0 or d naught or whatever, and then the alternative is mu1 minus mu2 is not equal to d naught, that just opens it up to, say you wanted to ask the question if the two population means differ by a particular number. Rather than putting 0 in for d naught, you could just put in like 5 or something, and then you would run your hypothesis test to see if mu1 differed from mu2 by specifically 5 units. Okay, more than likely, all of the questions that we're going to see and that we're going to use are just going to be basically where d naught is 0, but it's given to you in this formula just in case there's a reason to not look at to not just equate them or differ them. If you want to like add in some constant there to where they are differing by that amount, you could do that. That might come into play in your case. That's kind of up to you when you come up with your research questions. Maybe you see some reason that you think like 2 of the samples could differ by some specific constant. If you come up with a reason for that that makes sense, good for you. Like that's fine. But more than likely, you're going to use d naught equal to 0. Okay. So hopefully you guys have this worksheet in front of you, because the formula, when I converted this document over from a PDF to a Word document, did not show well. So I'm actually going to pause the video and try to find the document better so that I can just walk through this. And we're back. Okay, so yeah, I got the PDF version of it, so it's much easier to read, and this should be what kind of like you're looking at on your worksheet as well. So the formula that we're going to use, and this is us assuming that we have unknown population variances. Okay, so this automatically we know is t, and that the population variances are assumed to be equal. Okay, so we see case 1 assumed to be equal. We're actually not going to get into the case where we assume that they're not equal. Formulas for that are in the book. It looks like on page 376, but that's just going to be for your reference. I'm going to be focusing on we assume that they're equal, just because these formulas get really big and really convoluted. And quite frankly, I just don't think we have enough time to learn the different ways and for you guys to be comfortable with it, given that the formulas are really, really, really cumbersome. Okay, so this, just taking a look at this test statistic, t is equal to x bar 1 minus x bar 2, whole thing minus mu1 minus mu2, and that's over s1 squared n1 minus 1 plus s2 squared n2 minus 1 over n1 plus n2 minus 2 and the square root of that, and then that's all times the square root of 1 over n1 plus 1 over n2. Okay, so these are a huge formula, but this is the test statistic for this distribution, and this would be the distribution that we would equate to what we learned in 9.2 and 9.3. More or less 9.3. We don't exactly have a version. Like we're not going to be working with a z statistic, I don't think. Yeah, we're not going to work with a z statistic. I'm looking through just to make sure. We're not working with a z statistic that's going to be about a mean in chapter 10. So we're just working with t. And yeah, so this really is kind of the extension of 9.3. So take a look at that formula, and you're going to need to know how to use this formula. Yes, you might have to do it on a test. The good thing is we, a lot of the time, are going to give you output. So you're just going to have to analyze the output. And that obviously is going to be fantastic for you because you won't have to just do a bunch of this calculation, arithmetic, all that stuff. Okay, so right here, SP squared is equal to whatever is underneath this square root here, as you can see this formula. So this formula will break down a little bit easier. Here, let me transfer back over here. There we are. And that formula, from what we had just saw, is going to look like t x1 bar minus x2 bar mu1 minus mu2. Right, so this is the difference between mu1 and mu2. And a lot of the time in our h naught, we're going to propose that this difference is d naught, which is 0. So a lot of the time, the top of the fraction is just going to be x1 bar minus x2 bar. Okay, and so then I'm just going to put sp here times the square root of n1 plus n2. Okay, so it's going to start to look like this. This might then just be 0, right? More than likely, that's what it's going to go to. And this formula is going to kind of break down from the thing that's just ridiculously convoluted and so many letters and numbers and all that stuff to essentially x1 bar minus x2 bar minus 0. So just x1 bar minus x2 bar all over the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. Okay, we'll see how to use that in a little bit here. Okay, so let's just work on an example. This is how I generally teach, obviously, and let's just do this. An instructor is interested in comparing the characteristics of students who do and do not work full-time during the school year. Specifically, she is interested in whether there is any difference in terms of their GPAs. Assuming that each of the underlying populations of GPAs is normally distributed, use the information below to test at alpha level equal 0.05 whether the students differ in terms of GPA. Assume for now that the population variances are equal. We actually test this assumption later. Okay, so like I said, we're not going to worry about this whole thing. We're kind of just assuming that always. And the students differ in terms of GPA. Okay, so what does that mean? Differ. Not that one group is higher than another, right? I think the kind of cognitive assumption that we make is that the people who don't work should be higher than the people that work just because they would have more free time or something like that. But this is not what this is saying. This is saying differ. So differ implies that we're looking at an equal, not equal scenario. Okay? All right, and lucky for us, all of the statistics that we need are calculated for us. So this is what we're going to see a lot of time. A lot of time we're going to put this into Megastat, and it's just going to give us a bunch of stuff that we can use. Okay? So I'm going to go ahead and start this problem, and then we're going to learn how to essentially use all of this printout information that we have. So the first thing that we do in any hypothesis test is we're going to state the hypothesis. So we have an H naught and an HA. Okay, and a couple different ways that we can state this, but because we said differ, we're not differing by any factor other than them being equal or not equal, right? So this D naught that we were looking at is just going to be 0, just like I kind of mentioned. So one way to write this hypothesis test is mu1 minus mu2 is equal to 0. And the alternative is mu1 minus mu2 is not equal to 0. Another way to write this would be H naught, HA, and we could just say mu1 is equal to mu2, and mu1 is not equal to mu2. Take a second, look at those, and just kind of remind yourself why those are the exact same thing. Okay, I tend to think that the second way is a little bit easier cognitively. I think that it's a little bit easier intuitively to understand, but that's just me. So I'm fine with either way that you want to write these. Okay, either way that you want to write them. But note that the second way of writing them you almost have to have that d naught, the difference constant, to be 0. You just have to be comparing them and assuming that they're equal and not equal, that sort of thing. Okay, so 2 is always us talking about our significance level. What significance level did we say we were using in the problem? 0.05. So let's do that. So alpha level of 0.05. Number 3. Okay, so this is the t-test for comparing means. This is the one that we just learned, obviously. T-test for comparing means. And I'll let you guys write out that big long statistic. I'm just not gonna. So, but yeah, the statistic that we would be writing out is, well, goodness, is this one. Is t is equal to all that stuff. Okay? All right. So, number 4. Number 4 is where we establish what our rejection region is. So, because we're working with the t-distribution, we know that the curve is going to look something like the normal distribution, right? The t-distribution curve is a little fatter, has fatter endpoints, but essentially a similar shape. And obviously, if you're writing this out, there's going to be essentially no difference. So we'll establish our rejection region. So because we're equals not equals, we know that it's two-sided. And because our alpha level is 0.05, we know that we have 0.025 right here, 0.025 right here. So this is an RR, a rejection region, and so is this. And this is 0.95 here, and this is our fail to reject region. Okay. So one thing that we've got to do then is find where our t critical values are, right? So let's find t crit. We're going to have 2 of them because we have 2 different rejection regions. So we're going to have a t crit value positive and a t crit value negative. And one is going to be, so remember what we do is we always have t alpha half, comma, the degrees of freedom, right? So the degrees of freedom for this type of distribution is going to be n1 plus n2 minus 2. Okay, so that's how we calculate degrees of freedom here. So let's go up here and just calculate this for the heck of it. So how big is our sample? We have a sample of 6 for n1. So n1 equals 6, n2 equals 7. And so then n1 plus n2 minus 2 is going to be 6 plus 7 minus 2, which is 11. So degrees of freedom equals 11. And our alpha half is 0.025. So 0.025, 11. So we're going to look in our table. Where is our table? Oh, it's here. Let's look in our table, T table. Degrees of freedom 11, and T of 0.025 is 2.201. Okay. Uh-oh. Hope I didn't screw the pen up there. Okay. I didn't. 2.201. And for the negative version of that, we have a negative 2.201. Remember, the T table is a little different than the Z. You look it up, and in the inner portion of the table is our critical values, whereas like the Z table, you look up critical values, and then the inner portion of the table are probabilities. Okay. So we came up with our critical values, and so then we say reject if t calc or t data is greater than t crit plus that's equal to 2.201, or reject if tcalc or tdata is less than tcrit negative of negative 2.201. Okay, so that's our rejection region. I'm running out of space here, but I'm determined to get this in on one piece of paper. So, yeah. Okay, so 5 is when we calculate stuff. The good thing is all of the calculations have been done for us, right? We have a bunch of output, so we don't actually need to calculate any stuff. So we'll just say output. And so then we'll just say what our tcalc is. So our tcalc is what? Let's go up here. Our output has established that our t-value is negative 0.908. Okay, so the question then is negative 0.908. Is this in a rejection region? Is this greater than our t-crit plus of 2.201? No, right? Is this less than our t-crit negative of negative 2.201? No. So this t-calc value is going to fall somewhere like here-ish, right? So it is not in a rejection region, so we would say fail to reject. And we would just say there isn't significant evidence that that students that work have different GPAs comparative to those who don't, right? If we thought that this data had given us a conclusive, evidence or significant evidence, however you want to put it, then we would have had a t-calc value that would have been in our rejection region. It would have surpassed one of our critical values, right? So we failed to reject. So this, as you can see, this problem operates very, very, very similarly to the ones that we did before. The only difference is we're using two samples, and we're comparing those two samples as opposed to comparing one sample against like a value. All right, guys. Well, let me know if you have questions on that. Now we're going to move on to two samples that are paired. Okay, this is kind of a cool thing. This type of hypothesis test is a hypothesis test where you're essentially like measuring cause and effect. You guys can take a moment to read it. It's called matched or matched pairs or pair samples, or there's all sorts of names for it. But essentially the idea is that both samples have the same size, and you are calculating a characteristic about each data point, and then you're seeing how that characteristic has changed over time or given some different scenario or whatever. But essentially there's going to be, the data point is going to have one characteristic, and then it is going to be directly paired or directly linked to another data point that then is like differs based upon time or something like that, and then there's a new observation, right? So it would be like, I guess to bring it back sadly to this last election, like if you were watching one of the presidential debates and they asked you on a scale from 0 to 100, what are your thoughts about Donald Trump? 0 being can't stand him, 100 being I love him, 50 being okay. And so then prior to the debate, you were asked that question and you gave some sort of number, okay, and then after the debate, you were asked that question and then you gave some sort of number, okay. Your data point, there would be two data points from you. You're the commonality. You're the link there, right? So each data point has a corresponding data point on the other side, essentially. So these are the types of tests where matched pairs make sense. The cool thing about this is while this is a two-sampled test, it actually operates as kind of like something from Chapter 9, kind of like a one-sample test, because what we're doing is we know that both n's like n1 and n2 are the same, because you can't have you can't have one without the other, essentially. Right, like you can't have a secondary opinion about something without actually having a first opinion on it, that sort of deal. Okay, so what we end up doing is we end up taking the difference between those numerical data points. Okay, so that difference then becomes the number that we're looking at, and then we compare it to some number, some d naught, right? And newsflash, we're probably going to be using a d naught of 0. Okay, so here are the formulas for this. They didn't turn out too bad comparative to the PDF, but I will click on over to that. So if we look at this t of nd minus 1, so we have d bar, which you can kind of equate that to x bar, and then minus d naught, so this would be like our proposed difference, and that's going to be over the standard deviation of d, so the standard deviation of the difference, divided by the number n sub d, which is going to be the number of differences. So not the total number of data points, but the number of differences, right? So essentially it's going to be the total number of data points divided by 2. So that's that. So this formula, if you were to replace the little d with x, it's going to look almost identical to the formula that we used in 9.3. Right, so you'd have x bar minus mu naught divided by s of x divided by n sub x, or just n. So this is going to run fairly simply, and let's just do an example on it. Okay. A mathematics aptitude test was administered to 5 students, both before and after taking business statistics. Assume that individual scores on this test are normally distributed, and test at an alpha level of 0.05, whether taking business statistics improves scores on the aptitude test. Okay. So we have student 1, student 2, student 3, student 4, student 5. Sorry for the formatting. I know that's terrible. But the before stats and the after stats, and I'll go ahead and work this out. I know that we have a printout on it. We have some computer output on the next page, but I just want to show you how we would work something like this out. Okay, so we'll just go ahead. We can tell it's matched pairs because we have before and after. Essentially, we have a condition that gets applied, and then we kind of rerun the numbers. So I would just take the diff, which I would just call this, if we wanted to call this our x sub 1, and then we could have x sub 2, and this would just be x sub 1 minus x sub 2 sort of deal. So our diff right here, actually, let's run it the other way. No, that's fine. Are we running it that way? Yes, let's run it the other way. Okay, so we'll just say it's x sub 2 minus x sub 1. That'll be the difference. Because we kind of assume that the secondary score is going to be higher, so we would then be working with more positive numbers on the diff side. So, okay, so the first student got a 96 on the test prior to, then after taking business stats, got a 94, so that's not good. So we have a minus 2, 4, 5, 6, and 5. So 4 out of the 5 students had an uptick on their score, so that's kind of what we would expect that. So we add up these differences, we get 18. So then if we want to find d bar, it would just be the average. So 18 divided by 5. And that gets us 3.6. If we want to find the degrees of freedom, which we'll need, it's going to be the number of differences minus 1, which df is then equal to 5 minus 1. Okay, so that's that. All right. So now let's run our hypothesis test. Uh-oh. There we go. All right. So we want to know, did this, so let's see, mathematics aptitude test was administered to 5 students both before and after taking in business stats. Assume that individual scores on this test are normally distributed and tested at an alpha level 0.05, whether business statistics improve scores on the aptitude test or not. So we want to know, did it improve scores? So our alternative hypothesis, we'll start with that, is that we think that the mu of D is greater than 0. And then thus the opposite of that for our null, our status quo, is less than or equal to 0. Okay. What's our significance level? Alpha equal 0.05. What's the test statistic? We'll say t-test for matched pairs. Okay, and you guys can write out the t formula if you would like. Okay, and then the fourth thing is we establish our rejection region. Not bad right there, right? Okay, so because we are just looking greater than, we know that our rejection region is going to be just one-tailed, and it's going to be to the right, because this is a greater than. So this is our rejection region. It's going to have all of our significance level, all of our alpha in the tail. So 0.05 right there. And so we have 0.95 here. So this is our rejection region. This is our fail to reject region. Great, my pen is being silly again. Okay, so we have a t-crit right here. What is that t-crit going to be? Well, so that t-crit is going to be based upon the degrees of freedom and the alpha level. So we use all of the alpha at this point, right? We're going to be using 0.05 because we want to have it at this point. And this is the point where 0.05 is beyond it. So t of 0.05, comma 4. We go to our table for that. Degrees of freedom 4. 0.05 right there. We get 2.132. So we just have a t-crit positive, right? We don't have a t-crit negative because this is just one-tailed. So then we end up saying reject if t-calc is greater than t-crit, which is equal to 2.132. Okay, so that's that. And so now we are going to run our calculation. So t-calc is equal to, let's go back up and look at our formula. So it is t is equal to d bar minus big D naught divided by, oh gosh. All right. So I guess I just showed you some of the work. We actually will use the output on the other side because I'm not about to like calculate a standard deviation here. So yeah, so let's just go to the next page. The next page has all the output. So in the next page, we have the mean of 3.6, which is what we calculated, right? And we have I wish this printout would have went better. Let's look at it here. There we are. With the mean of 3.6, we have a standard deviation of 3.209, n, degrees of freedom, t-value, all that kind of stuff. Okay, so we're going to use this. This is the printout. This is the one that you guys will be using. You're not going to have the Word version. For whatever reason, the formatting is just silly, and I can't use the pen on the PDF version from this computer, so we are relegated to me, unfortunately, using the Word version, which sucks, but whatever. Okay, so we ran all of our hypothesis tests here, and this is our output. So our t-calc value is 2.508, right? Yes. So 2.508. All right, so then now we say, is this a reject or not? Is this in the rejection region? Okay, we go back up to what our specification is. We say reject if t-calc is greater than t-crit of 2.132. Well, t-calc is in fact 2.508, which is greater than 2.132, so we reject. So we reject the null hypothesis. And say reject because t-calc equal to 2.508 is greater than t-crit, which is equal to 2.132. And then our number 7 conclusion is there is significant evidence to suggest that scores improve after taking business statistics. So that's that. Yeah, sorry guys about this. This is frustrating to me that this output is so poor. I'm not quite sure. When you convert something back from a PDF to a Word document, kooky things happen. I don't really know why, so that's that. So we'll move on to testing differences in proportions. Again, let me know if you have questions on the discussion boards. That is the best way to do it. All right, testing differences in proportions. I will go to here to explain it to you because this is organized much better. And so now this is just going to be the Chapter 10 two-sample equivalent to what we did in 9.4, which was the z-test about the population proportion. Okay, so this should look a little bit familiar to you. In 10.1, we had similar hypotheses that looked like this, that were, using mu1 minus mu2. Now we're just changing that to p1 minus p2. Okay, and our test statistic, our z, is very simple, right? It's just going to be not x1 bar minus x2 bar, but p1 hat minus p2 hat. Then that's going to be all minus the difference that we suppose that there is. More than likely, we're going to be using 0 for no difference. And yeah, that's that. So now then the complicated thing is calculating what this sigma p1 hat minus p2 hat is. And that's just this formula down here. Okay, sample 3. At a large company, a random sample of 200 males with 4-year degrees revealed that 130 had received a promotion within 2 years of earning their degrees. A similar group of 100 females yielded 50 promotions. Can we conclude the presence of discrimination against females at an alpha level of 0.05? Okay. Yes, I know that this table is terrible looking, but bear with me. Hopefully you have the other one in front of you, and hopefully it is working. So, as you can see in the table, sort of, P1 is calculated, and that's just going to be the proportion of males to receive a promotion within 2 years. And so out of the 200 males, there's 130. So 130 over 200 is going to be equal to P1 hat, and that's just going to be 0.65. Similarly for women, P2 hat is just going to be the number that got promoted out of the total number that were taken into account. So 50 over 100 or 0.5. Okay, so now we run our test. So the first thing that we want to do is come up with our hypothesis. So we have H naught or HA. And when they say discrimination, what does that mean? Okay, so we clearly are thinking that, or given the sample that we're looking at, we want to know, or we can clearly see that men get promoted at a higher rate from the sample. But we want to know, is this just sampling error? Is this just something that, actually just happened at random here? Or do we have significant evidence to show that there's discrimination going on? Because out of 200 and out of 100, we don't know. Say there was 2 men surveyed and 1 woman surveyed, and she ended up saying, "Oh no, I didn't get a promotion," and both of them said, "Yes, we did get promotions." Okay, so that would be 100% for men and 0% for women. But is that really enough evidence to show that discrimination is going on? We would have a sample of 3. So like that's the idea. The idea is that like using the information that we have, using the p-values that we get from this, or the proportion values that we get from this, in accordance with the sample size, that's how we're going to determine if there's something more going on here in the population, meaning like overall. Okay, so discrimination would really mean that like on average, if we suspect discrimination, that the population proportion of men would be higher than women, right? So that would be P1 is greater than P2. Okay? I don't know if you guys heard that. Sounds like somebody's running a chainsaw outside of my house. Okay. I probably won't edit that out just because we're trying to roll through here and get it done. Or just riding a dirt bike, I guess. Okay. Anyways, so then the H naught would just be the complement of that. Okay? So then that would be P1 is less than or equal to P2. Okay. As always, you could do the other formula where it's just P1 minus P2 is less than or equal to 0, and then the HA would be P1 minus P2 is greater than 0. You can do that, but we're just going to leave it at this just because it's more intuitive, I think. Okay, so step 2 is what is our significance level? Alpha 0.05. Step 3 is what test are we using? So we're testing, say, test the difference in proportions. Okay, and then Z is equal to P1 hat minus P2 hat minus the difference, the proposed difference, over sigma P hat 1 minus P hat 2. So that's our test statistic. Okay, so 4 is we establish our rejection region. So as you can see, this is a Z statistic. So we're writing a normal table or a Z table. So something like that. And because we have a significance level of 0.05, and because it's a one-sided test that's facing the right, we have 0.05 over here on the right. Okay, so this is our rejection region. And then our fail to reject region has 95% of the probability. And so then we are going to be looking for the Z value. So for our Z crit, we'd be looking for the Z value such that 0.05 of the probability is to the right of the curve. This is one of those values that we just know that we have worked with a bunch. So you guys should have it memorized, 1.65. All right, so this would be the value that is equated to an alpha level of 0.10, like when we're doing a confidence interval, right? We would have 10% of the probability on the outside of the confidence interval. We just have 5% on one side now, and we're just working with a one-sided test. So then this would be reject if Z calc is greater than Z crit, and that's of 1.65. Okay. So 5 is where we calculate everything. Lucky for us, we actually don't really even need to get into that too much. We are just going to look at this table, which is again not showing what we want it to show. So I will hop on over to the PDF version of it. This table gives us a z equal to 2.5. Okay, so zcalc is equal to 2.5. This, hopefully this video isn't as choppy as it feels like to me, because presumably you guys are going to be looking down at your worksheet, your piece of paper, and your worksheet is just going to have all the good stuff on it, right? So you're going to be actually looking at the 2.5 value, whereas I have to go back and cycle back through it. Okay, so that's that. So then we determine, okay, what's our conclusion? So that's actually a 5. So this is 6. So do we reject? Do we not reject? Well, we go back to our rule here that we established in 4. We reject if zcalc is greater than zcrit, which is 1.65. 2.5 is greater than 1.65. So we reject. Because zcalc is greater than zcrit, and that's obviously 2.5 is greater than 1.65. And we can conclude that there is significant evidence to suggest that there is discrimination happening, right? So we get a z-value that's somewhere over here. So then we can look at this p-value, this 0.0062, and this is then, you can think of this 0.0062 as the probability that no discrimination is happening, right? So then you can think about that as, well, what's the opposite of that? The opposite of that is there's 0.9938 probability that there is discrimination happening. That's what we tested for. Okay. All right, now we move on to the final distribution that is new that we're going to learn in Chapter 10. And I will head on over to the PDF so I keep my sanity. And this is sections 10.4 and 10.5. They did the exact same thing in the book that they did in Chapter 9, where in Chapter 9 they took 2 sections to describe the chi-square distribution. That was where we were comparing a sample standard deviation against a proposed population, or a sample variance against a proposed population variance. And I said something like, I don't know why they split this into 2 sections, but they do. They did the exact same thing in Chapter 10. So in Chapter 10, now this is comparing 2 variances against each other. So we have 2 sample variances. And we're going to see, hey, are their population variances the same? Are they equal or are they not equal? Okay. And they take 2 sections to do that as well. Only difference is we're now not using chi-squared. We're now using a different distribution called the f-test. Okay, but this is the natural progression of the chi-squared table. This is just for 2 variances. Okay. Take a moment to look at the formula. The formula is extraordinarily simple, which the chi-square formula was definitely simple as well. But this is essentially just taking the larger standard deviation, or the larger variance that we get, and dividing it by the smaller variance that we get. Okay. That's that. And so then I'll show you how to use the F table as well. So let's just run a problem. You guys can read up on it if you want, but this test, this test operates very, very similarly to the chi-squared test, except that it's a 2-sample test. Okay, sample 4 problem, problem 1 revisited. Okay. Perfect, perfect, perfect. All right, so now sample 4, problem 1 revisited. An instructor is interested in comparing the characteristics of students who do and do not work during the school year. Specifically, she's interested in whether there is any difference in variability of their GPAs, assuming that each of the underlying populations of GPAs is normally distributed. Use the information below to test at alpha level 0.05 whether the students differ in GPA of variability, right? So now we're not looking specifically for the means, the population mean or whatever. We're now wanting to compare their sample variances or their sample standard deviations and compare those to see if their population variances do in fact differ. Okay, let's go. So looking back over here, okay, this is the output that we have, right? So we have a variance of work, variance of don't work, and we have an F statistic. So let's go ahead and set up our problem here. Okay. We have H naught, HA. So the status quo is to assume that they are the same. And then the alternative is going to be, we kind of want to prove that they're different. So we have sigma squared 1 is equal to sigma squared 2. Or, sorry, is not equal to sigma squared 2. And then the status quo, or the null hypothesis, is going to be sigma squared 1 is equal to sigma squared 2. What's our significance level? 0.05. What test are we going to be using? The compare to variances test, which is the F test, which is denoted as F, which is degrees of freedom of 1, degrees of freedom 2 is equal to S1 squared over S2 squared. And actually, I'm gonna sub these differently. We're gonna say work and don't work. You'll see why in a second. Okay. Because the way that this test goes is you always want the larger variance on top. All right. So number 4 is we're going to establish the rejection region. When you guys get a chance to bop on over to the table, you'll see that the table looks very much like the chi-squared table. It is like this. It's not at all like a normal table. So let's establish our rejection region. Because we have an alpha level of 0.05, we're going to have a rejection region of 0.05 right here. Okay, so we have a FTR, fail to reject region of 0.95, rejection region of 0.05, and we are going to call, so we need to find what our F crit value is. So F crit is going to equal F of the degrees of freedom of the larger value. So we can say degrees of freedom large, comma, degrees of freedom small. Okay, so what are our degrees of freedom here? 1, 2, 3, 4, 5, 6, 7. So work is our, first of all, we'll look at these statistics. Work is our larger variance. Okay, so this is going to be the thing that goes on the top of our fraction. Okay, work. So let's, we can assume that work is the, so because work is the larger variance, that's going to be the first, that's going to be our numerator, right? So that's going to be the first degrees of freedom that we look for in the table. So there's 1, 2, 3, 4, 5, 6, 7 pieces of data. So the degrees of freedom for that are going to be 6. And now there are 6 pieces of data for don't work, so the degrees of freedom of that are going to be 5. So for degrees of freedom, so this F statistic is going to be F of 6, 5 with an alpha level of 0.05. Okay, so let's go to the F table. Oh, so yeah, and then these tables are set up a bit differently. Like each table is its own alpha level. So this is the table for 0.10 alpha. Now we got to look for the 0.05 alpha right here. So this table right here. Okay, and so then we have degrees of freedom 1, which is the numerator. We're going to come across the top. So that's 6. Okay. And degrees of freedom 2 was 5. So we go down here. Okay. Oh, there we go. I was looking at the wrong one. So 6 and 5. So 4.95 is our F value. So 4.95. So again, we reject if F calc is greater than F crit, which is equal to 4.95. Okay, so yeah, I'm again determined to finish this on one page. And what is our F calc? So F calc is just going to be the well, I guess we can show the calculation, or we can just show it up here. So it already calculated it for us, but I'll just show you how to do it. So we know that our F calc is 1.29, but that is just then our variance for work, which is 0.2149, divided by our variance for don't work, which is 0.1671. And that's going to equal 1.29. So that's our F calc. So do we reject? Is 1.29 greater than 4.95? No. So we fail to reject because of what I just said. Because F calc is not greater than F crit of 4.95 and 1.29. And then, so then what do we say? We cannot conclude that the variances are different. That's it. Okay, I am going to not go over sample problem 5 in the video, though when I put the solutions manual up on Springboard, I will have the solution for it. That's just for time's sake, but that's going to operate exactly the same as problem 4 did. So you'll have the solution there, but I'm just not going to cover it in the video, guys. If you have any questions on this material, please feel free to ask me via email or on the discussion boards. I know I say it a million times, but I just want to make sure that you guys use those resources because it helps other people to answer questions. I wanted to get this out to you today. I know we don't start really covering this stuff, and you have a test this weekend, but I wanted to get this to you today so that in case you and your group were working on the case, this is the last piece that you need for the case. This is the last notch in your tool belt that you need for this case. Okay, so go ahead and shoot me any questions that you have. If any groups want to meet with me, I'm available on Tuesdays and Thursdays. You just have to set up an appointment. Okay, so email me and let me know. Don't wait to the last minute with this case. That would be very, very bad, and I won't be too happy about that. So, all right, let me know if you have questions, and until next time, thanks so much, guys.